Welcome to the second part of the Applied Mathematics course for chemists and mathematicians. In this part of the course, we are going to take a closer look at the kinds of functions and operators that you will work with in the physical chemistry course. So we're going to extend the theory a little bit, and we're going to actually work problems that are very closely related to the problems that you will work in physical chemistry, so you're better prepared for them. So we're going to start off today talking about operators. And when we talk about operators, we will often designate them with a special letter, such as this A with a hat on it. Operators are actual physical entities. So let's make a list of the physical entities in quantum mechanics that are operators. So the operators that we're going to talk about are the operators of quantum mechanics, and they are entities, physical entities like momentum, kinetic energy, position, and angular momentum. I'm going to write down the Schrodinger equation in operator form on this next blackboard, and we're going to identify where the operators are and what they are operating on. So here is the Schrodinger equation in operator form. The operators are on the left and the right side. This H hat is the Hamiltonian operator, and the operator E on the right hand side is the energy operator. Operators act on functions, and the function that these two operators are acting on is this function psi, and that is a wave function. So we'll come back to this Schrodinger equation later on in the course. Let's take a closer look at operators, though, by looking at some operators that with which you already are familiar. So we have that operators act on functions, and we looked at the Schrodinger equation, which had the Hermitian or the Hamiltonian operator and the energy operator. But let's look at two very familiar operators before we think that operators are more abstract than they really are. So those two operators are the differential operator, which we're going to designate with a capital D and a hat over it, and the integral operator. And we'll designate the integral operator with a capital I and a hat over it. Notice that we have a placeholder designated with a dot here for where the function will go that we're acting on. So let's see that the differential operator is an operator, and let's also see that both of these operators are linear operators. So let's first define what a linear operator is, and let's see that the differential and the integral operators are linear operators. So we're defining the linear operator A, and it is acting on this combination of functions. So f1 and f2 are functions, and c1 and c2 are constants multiplying those functions. So we're asking we're defining what happens when the operator A acts on c1 f1 plus c2 f2. If the operator is linear, here's what happens. So when an operator is linear, it means the operator acting on the sum is the sum of the operators, and the constants move out front. So here's the result, or the way we can simplify an operator that is linear acting on the sum of functions. So in words, the operator acting on the sum or constant time sums is the constant times the first plus the other constant times the second. And let's see that the differential and the integral operators are in fact linear operators. So we're going to take the derivative of a constant times the function f1 plus a constant times the function f2, and we know that that would be c1 times the derivative of f1 plus c2 times the derivative of f2. And if that's not clear, let's show it by an example. Right, so if we're taking the derivative of 5x cubed plus 11x to the fifth, we know from calculus 1 that is 5 times the derivative of x cubed plus 11 times the derivative of x to the fifth. So the derivative operator, I hope you're convinced, is a linear operator. That is, it follows this linear operator guideline. Let's see if the same is true for an integral operator on the next blackboard. So we can actually use the same example, the integral operator I acting on 5x cubed plus 11x fifth, the same function set that we used in the last example. That would be the integral between a and b. The 5 comes outside, integral x cubed plus 11 comes outside, integral a to b of x to the x to the fifth. So the integral operator is linear also. Or if we put it in formal language, the integral operator follows these guidelines that we showed here in this example, why that's the case. However, it is by no means the case that all operators are linear. Let's take a simple operator that we'll call the square operator, meaning we square what it's acting upon. So if we square c1 f1 plus c2 f2, constant times f1 plus a constant times f2, and actually I want to pause for a second here and make a note that when c1 f1 plus c2 f2, it means c1 f1 plus c2 f2, that sum of functions squared, which is going to be FOILed, right? So it's c1 squared f1 squared, that's first. Inner plus outer is this twice, so it's 2 c1 c2 f1 f2 plus c2 squared f2 squared. So the question is, does this equal c1 square f1 plus c2 square f2? And it should be fairly obvious that it does not. We have to take a closer look at what we have here below to see that it does not. You can actually identify several problems, right? Here's the here would be the square of f1, so this part is okay, and this part is okay. So those f1 and f2, those are okay, that's what we want. That's the square of f1 here and the square of f2 here. But here's the problem, right? c1 is squared and it's not supposed to be squared. c2 is squared, it's not supposed to be squared. And then there's all this other stuff that's not even supposed to be in there. So the square operator is clearly not linear. Okay, so we're going to have this video draw to a close and pick up other topics on operators in the next video. But I want to look at what we're going to do in the next video, and that is what we call the eigenvalue problem. So we're going to have an operator A, and that's going to act on a function psi. I'll put the of x in there this time. And we want that operator to be such that when we do that, we get the function psi back and a constant a. And this is a particular kind of operator This function psi has got a special name. So the fact that the function psi shows up on both sides of the equation, it's called an eigenfunction. The eigen is the German word equal, so that's sort of explaining why that is. And this whole problem, a psi of x equals lowercase a times psi of x, that's called an eigenvalue problem. So there's a number of important operators in quantum mechanics that involve eigenvalue problems, and we're going to look at those on the video that follows this.